Okay, good evening, everyone. In last classes, we have learned what we will be learning. But from now on, we will try to go into the subject. So we want to learn something regarding the course. So first chapter, we will be learning about the kinetic molecular theory of gases. Even in the first class, I have mentioned something about the kinetic molecular theory. That means how the size of the molecule or the molecules and the space in between, what would be the interaction or attraction force between the gases. So we have several things to learn regarding the gases. So first we will learn the kinetic molecular theory, and addition to this we will learn several gas laws like as Charles gas law, Boyle's law, and then some Avogadro's law, several other things, and then we will try to combine the formula together so that we can get the ideal gas law, and then we will try to get the kinetic energy of the gas molecules. So that would be the class for today. So let's start. What is the kinetic molecular theory? Before going there, we need to get some idea, a closer look about what macroscopic gas behavior at the level of individual particles. We will learn and explain the gas law mathematically. We have some questions we need to think about, and we need to understand the answers of these questions. What are the questions regarding the gas behavior? First, how please. Have you ever seen you can erase the pen color also? Have you ever seen a pen like this? We can erase what you write down by your pencil in your paper, but you can erase what you write in your pen. That is also possible. Not fluid, like a pencil. Yeah, that is something. Yeah, just like a pencil. Yeah. So I tried to clean up the board, and I'm thinking, oh, if I can clean that also. Anyway, how individual gas particles contribute to total pressure? We have multiples of gas molecules in a container. Then, how the individual molecule contribute to the total pressure? If there are 5 molecules inside the container, how much would be the pressure? If it has 500 molecules, then if the pressure will remain same or it will increase, how it can increase? What is the contribution for the gases to in the volume or pressure, something like this? We'll try to learn. Pressure is a measure of the force exerted on container surface. You may have a bigger container or a smaller container. That means, what is the pressure? Pressure means how much force is applying on a surface. Just if you have a container like this, you may have a very big container or very small container. Now, if you have the molecule here, this substance has some surface. Now, how much force the individual molecule is applying on the surface? Collectively, we can consider that is the pressure. So how much force is applied to the surface of the substance or wall of the substance, that is collectively known as pressure. What happens when external pressure compress volume? Now, if you press the molecules from outside, it can be from one side or it can be from everywhere. So, if you press the container externally, what will happen? Maybe we can have like this way. If we compress the container like this, in that case, maybe we can have a container. We can reduce the volume like this way, and then our molecules had previously quite long space. Now we may have little smaller space. Just if you consider the space between these two molecules, right now it is quite small. So that can happen. So what happens when external pressure compresses the volume? So that can be explained by using a certain law, the name, the Boyle's law. At a certain temperature, the volume of the gas for a closed container is inversely proportional to the external pressure. That means volume is inversely proportional to the pressure at constant temperature. We'll write down at constant temperature. So we will learn that one little bit more. And why is gas contribute to total pressure in proportion to mole fraction? That means if we remove one molecule, then the pressure can be reduced a little bit. So how much pressure it is exerting when many molecules are there, and if we remove some of them or if we add some extra molecules, how it contributes, why gas contribute to total pressure in proportion to mole fraction. That means as the number of molecules are increasing or decreasing, their pressure will increase or decrease depending on how much molecules we are increasing or decreasing, and that will depend on the proportion to the mole fraction. Okay, that can be explained by using the Dalton's partial pressure law. We'll learn that. What does temperature measure? How temperature affect on the molecular particle scale, and that is the Charles law. We will learn why 1 mole of any gas, maybe 1 mole of hydrogen, 1 mole of oxygen, 1 mole of carbon dioxide, whatever. For any gas, 1 mole of any gas has exactly occupy the same space and exert same pressure. We will try to find out this question. Not questions, we'll try to find out the answer of these questions. Okay. Now let's see. That is some formula. I'm sorry, because I'm quite a bit far away. So just pressure, temperature, volume relationship. Maybe I should have some animation. Okay. Here you can see that if you fix the temperature, and if you increase the pressure, the volume will be reduced. Again, if we go other way, just that is right now all the parameters are constant, fixed. Now, if you increase the pressure, the volume will be reduced. Again, if we reduce the pressure, volume will increase. So that will be like this way. So that is the when we increase the pressure, volume decreases. That means if we pressurize this container, that will become like this. That means the interaction between the molecules or intermolecular distance between the molecules will reduce. Is it? Okay. So by how it can reduce the volume, that is another way. So here we can see the Boyle's law, what we have mentioned, that pressure, here you can see the pressure is proportional to 1 by V or 1 over V. That means volume. That means pressure is inversely proportional to the volume. That means if you increase the pressure of a gas, then it will reduce the volume or other way. Then if we consider that the volume of the gas, later I think I have even more details. So if we go other way, if we reduce the pressure, the volume will go up. Here I have given the arrow. Just the volume will go up by reducing the pressure. I'm not going to detail yet because I have planned to discuss all the gas laws in detail little bit individually. So I'm going to the kinetic molecular theory model. There are some postulates. That means I think you don't need to write down. I'll give you all the notes. So just try to listen my words. That can be helpful. Again, I'm trying to record the video, but I do not know what would be the quality because sometimes I am in the camera and sometimes very far away, and voice can be a little bit low. Anyway,
You should stay near the camera, Professor.
sorry.
You should stay near the camera, Professor.
Yeah, if I want to be in front of the camera, in that case, I cannot see the board and I cannot show all of them, but I can try by this way. That can be difficult. Anyway.
Yeah, it's also difficult for us to understand.
Yes, I know. But I cannot cover up both of you, or I cannot make you satisfy at the same time.
Yes, I
That is a little bit annoying. If you do not have any serious issue, please join to the class. That can be even interesting. But until you can come back, please try to compromise a little bit. Anyway, what are the molecular theory? That means some property of the gas molecules have been thought that previously when scientists have worked with the properties of different gas molecules, they have found some special characteristics of that gas molecules. Mainly, this can be considered for the ideal gas. But actually, there is nothing ideal. Do you know? Nothing ideal. Neither human, nor any character, nor any food, anything. So, even what we are considering the kinetic gas molecular theory or ideal gas behavior, that are just imaginary consideration. So, first one, gas particles are extremely small. That is okay in some sense. But if you want to compare with some different gas molecules, in that case, one gas molecules may be oxygen and hydrogen. If you want to compare the radius of the oxygen molecule and hydrogen molecule, in that case, you can see that the radius are not very different. But gas particles are extremely small if we consider compared to a very large container. So we can consider that gas particles are extremely small. That is okay. In a constant random straight line motion, that means all the gas particles. Maybe I'm going to the next slide. That can be. Is not working. Okay. Maybe before going to that, what I have mentioned previously, that in a constant random straight line motion, okay, all the gas particles, here you can see many particles. These particles are moving randomly, just several direction. So in the next slide I will show you that how the particles, you see, randomly it is moving. So the particles are moving randomly. In random means there is no perfect direction, just up, down, front, back, anyway. Okay. So very large distance between particles. Maybe we can consider here. You can see that you cannot see the mouse. Okay. Here the particle size just this, but the space between the molecules from here to here, if we consider the size of the particle, the space between the molecule is quite large compared to the size of the particle. Then collide with each other or walls of the container. One molecule can collide another molecule, or even this molecule can collide this one. So the collide with each other, this molecule, one molecule can collide with another one, or even the molecule can collide to the wall. Okay, collisions are elastic. All of you are familiar with the word elastic. Yes. So what about here? Why you are using the word elastic here? That means you are familiar with that, the rubber or gather, whatever you are using in the air. So if you stress the rubber, then it can, if you remove the strain, then it will go back to original position. Okay. Then what about these molecules? It is elastic. That means the kinetic energy before and after collision are same. That is the term we are using for elastic. So in case of rubber, what you are giving, if you are using some strain so that it can stress, and if you remove the strain, it will go back to original position. So, but here we are using the word elastic to make understand that the kinetic energy of this molecule will remain same before and after collision. Okay. No forces between particles. That is very annoying. That means no forces between particles. That means what it has been telling, that this molecule and this molecule, they have no attraction force. If it is possible? What do you think? The color of the line is little bit different from others. No, try to explain, no problem. If you say wrong, that is also fine, because you came here to learn. Okay, yes, that can be. Okay. So if you consider they have same charge, then they can have repel each other. Then if they have opposite charge, they can have attraction force. Okay. But even without having same charge, they can also attract each other. How? If even, let us consider we have carbon dioxide molecule everywhere, all of them are carbon dioxide molecule or water vapor. So all of them are similar. So there is no way we can consider it is positively charged or negatively charged. Still, it has some attraction force. How we can prove that? Yes. So if it do not have the attraction force or intermolecular attraction, in that case, we could not have liquid water or ice. Always we will have the water vapor. So if you reduce the temperature of the water vapor, then you can make them cold, that means ice, liquid. And then if you reduce more temperature, if you cool more, then you can turn into ice. That means if there is no attraction force between the gas molecules, then you could not succeed to reduce the temperature, or you could not make them into liquid or ice. So that I have given the color that is not perfect. That means the postulate what? Again here, no volume. Particles are treated as point masses, no volume. So if they do not have any volume, then you could keep 10 liters or 1000 liters of gas in a small container. Is it possible? But you cannot, because we know that the cylinder what we use to store the gases, that is made of different types of steel or iron. So very big tank. But if you want to keep very large amount of gas in a small container, that is not possible. That means if they do not have the volume, that means these molecules, if the molecules do not have any volume, then you should be able to keep any amount of gas anywhere. That means any small or any big container. But as the molecules have certain volume, so you cannot keep a large amount of gas in a small volume. So all the gas molecules have some volume also. Then individual particle energy can change by collision. Okay, that is little bit contradictory. That means individual particle energy can change by collision. Here we have mentioned that the molecules are, or the collisions are elastic. That means if we say collisions are elastic, that means the kinetic energy before and after the collision is same. That is elastic. But here it is telling that the individual particle energy can change by collision. Contradictory? That means sometimes it can gain the energy or it can lose the energy. So that is little bit contradictory. The total energy stays constant. Yeah, that is okay. But that should be considered in terms of if the container is isolated or not. Isolated means, do you know what is the meaning of isolated? In thermodynamics, maybe you have learned about the 3 different types of systems: closed system, open system, and isolated system. Anyone remember?
They can't transfer the heat.
Yes,
From,
yes.
yeah.
Yeah. If the system can transfer both heat and substance, then this is called as open system. That means if you put a glass of water just without lid, then we can consider that is an open system. If you put a lid on the glass, or if you put a water in a a stainless steel or some metallic container, and if you put a lid, in that case, the water cannot
Closed
escape.
system.
That time, water cannot escape, but if you can have the temperature can be transferred from inside or outside. So that is known as closed system. And if you put the hot water or tea inside a thermoflask, then within very short time, you will see that the neither heat nor the matter, that means the substance, is transferring. So that should be isolated. So here we are considering if the system is isolated, no heat is transferring from inside to outside, or no molecules is transferring from inside to outside. In that case, the total energy stays constant. Another thing also we need to think about, that the temperature of the surroundings. That means if the temperature of the surroundings are different, in that case, we cannot keep the system isolated for a long time. That is one condition for the equilibrium. If you want to keep the system in equilibrium, in that case, you need to think about that the system and surrounding temperature should be always same. So we are not going to discuss that one. So total energy stays constant. This is more or less okay. Okay. Then what we have seen that already, particles in ideal gas have no volume. That is wrong. Have elastic collision. That is kindly wrong. That is, they have the, sometimes they can, if they have the kinetic energy different. Already we have mentioned that they can have different kinetic energy. That means individual particle energy can change by collision. So if you have this molecule have kinetic energy, it can gain the energy when it collides with this wall, or when it collides with this molecule, it can go far away from this. So it can gain some energy by collision. It has mentioned. Are all the kinetic molecules are in constant random straight line motion. Constant, that means the velocity will always be same. But have you ever seen that when two vehicles are colliding each other, then depending on their mass velocity, one will go very far away, another will can keep the same position. So if it is striking, if the molecules are striking on the wall, the volume of the molecule is very small compared to the wall or the container. Therefore, if you consider that it is striking on the wall and still it is having the same kinetic energy, that is not happening. So that is not correct. So let's see, don't attract or repel each other. Already I have mentioned that no, all the molecules have some kinetic energy, and also they can attract or repel each other, so that we can change the state from solid to liquid or liquid to gas or whatever. We are considering the gas, so we will think about we can compress the gas into liquid, and also it is possible to convert into ice. Therefore, it is not right. So don't attract or repel each other. That is not okay. Have an average kinetic energy directly related to the Kelvin temperature. Yeah, that is fine. That means if we consider the average kinetic energy, some of them can have very high kinetic energy, some of them can have very low, and some of them can have mild or in between. So that is okay. So, and then now, origin of pressure. How we can think about the gas molecule can have some pressure. Gas particles are moving objects colliding with the container wall, exerting force. Okay, we have some gas molecules inside a container. In that case, if you have the molecules, then all the molecules are moving randomly, already you had mentioned, and they have some kinetic energy, and they are moving and colliding each other. These two molecules, they are colliding and going far away, towards and far away. Okay, moving objects colliding with the container wall, exerting force. So if the molecules do not hit on the wall, that means if the molecules do not hit on the surface, then there will not have any pressure. But randomly, all the molecules are moving and all the molecules are having a strike or collision to the wall and even inside the molecule one each other. Therefore, we can have the force or pressure to the system. Greater the number of particles, higher the frequency of collision, more pressure. That is one statement you can consider. If you have few particles, let us consider 5 particles. Here we have given 1, 2, 3, 4, 5, 6, 7. Okay, we have 7 particles in a small container. So what is the possibility of having collision between them? If we consider one by one, maybe 2 molecules, this one molecule. So the possibility of having collision between these molecules is 1:1, like this. This molecule can have collide with this one or just at the same way. So the collision or possibility of having collision between these molecules is 1 by 1 or 1:1. But if you have 2 molecules of A and one molecule of A and 2 molecules of B, in that case, what is the possibility of having the yes should be 1 into 2. That means this A molecule can collide with B and A can collide with this B. So the possibility of collision is increasing. Now, if we increase another A, in that case, this A can collide with this can this, and this. So overall, we are having 2 by 2. So as the number of molecules increases inside the container, the possibility of collision increases. Therefore, the pressure also increases. So greater number of particles, higher the frequency of collision. You are familiar with the word frequency. Someone can you make me understand what is the frequency? Anyone from online? What is frequency?
No idea, Professor.
No idea. Okay. Someone from you? You need to mention some time. Is it in 1 second or 1 unit of time? Maybe you can consider. That means any event happening per second or per unit time. Always we will consider the time unit as second. Therefore, how many event happens per second? That is the frequency of that event. Okay. So if we have lot of gas, we can have the possibility to collide each other. If we have more number of molecules, then the number of collision is increasing. Therefore, the pressure is increasing. So what I have mentioned here, greater number of particles, higher frequency of collision, more pressure. Okay. Now, at constant temperature, external pressure decreases, the distance between particles, volume decreases, already what I have shown previously. So you can see from here, this figure, this is a container, this is also same container. This is a frictionless piston. That means you are familiar with the syringe. Some of you can have the different types of injection in your body using the syringe. So exactly same thing. So this is a piston. By pressing this piston from top, we can apply the force. We can apply some force to the, that means external pressure. Applying force, that means applying the. So now here you can see the total number of molecules. If you count the total number of molecules, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So here we have 13 molecules. And the volume is up to this level. You can see. Now, if you increase the force from the top to the using the piston, then the volume is decreasing here. So the volume has been, internet connection is unstable. Okay, so here the volume has been reduced to half, almost. But the total number of molecules, what was here, it is exactly here. That means you can see that the distance between the molecules from here to here, how much distance? Now here you can see the distance between these two molecules has reduced quite a lot compared to this one. That means the intermolecular distance has been decreased due to increase the external pressure. That means, so what happening? As the intermolecular distance is decreasing due to increase the pressure, therefore overall the volume of the gas has been reduced quite a lot. Previously it was up to this much. Now the pressure volume is that much. So we are increasing the pressure and volume is decreasing. Therefore we can have these types of formula. That means Boyle's law, the volume is inversely proportional to the external pressure. Okay, just or inversely, if we consider the pressure is inversely proportional to the volume. So if you have larger volume, that means if we consider here should be the pressure of the molecules is higher because we have more molecules in a small area, a small volume. Therefore, we will have the possibility to collide the molecules more compared to this one. Therefore, we will have more pressure in this area compared to this area because we have more spaces. If you want to move from here to the up to the wall, you need longer time, and if you want to move just one step, that takes very shorter time. So the number of collision will be more if the volume of the substance is large. Therefore, the number of collision will be less. Okay, so we can consider both way. If the pressure increases, here the pressure increases, the volume decreases, or if the volume increases, the pressure decreases. Okay, adding gas to, okay, here you can see this is a gas container. We have 5 molecules and here we have 4, 5 and 10. Okay, in the same size we have 2 different containers having one with 5 molecules, another with 10 molecules. Let us consider it is giving the pressure. Here you can see the meter, but exactly I cannot read the number. Maybe this is 2 up, this one 4, is it like this something? Anyway, whatever the number is, let's just guess. We have 5 molecules and 10 molecules, and if you combine the molecules together in the same region, when there are 5 molecules, that time it has some possibility to strike the wall or even striking themselves also, so that we will have certain amount of pressure. Again, we have these 10 molecules. Maybe we can expect that the pressure for this container would be double of this, because if we consider previously, as we have mentioned, as the number of molecules is high, the pressure will be high. So we are getting that we have twice the number of molecules compared to this. Therefore, we can consider that the pressure, but not exactly relation. We are imagining something. We are imagining. So this is the number of molecules and this is the number of molecules. Now it has certain pressure and this also has certain pressure. Now if you want to, if you combine both the gases in a container, in the same container, then how many molecules are here? 15. Therefore, we can easily consider that the pressure of the container will increase, because already we have an idea that as the number of molecule increases, the pressure will increase. Therefore, number of collision will be more, therefore pressure will be high. So now these 5 molecules also remain in this container, so it will have certain portion of the pressure. Is it? When these 5 molecules was here, now if these 5 molecules are kept inside this container, the volume is same, is still the same, because here, all the volumes are same. Therefore, if you have only the 5 molecules in this container, here we just consider you do not have the yellow one, just you have only this green or the blue, whatever. So 5 molecules, then the pressure would be whatever we had in this container. Now again same thing, let us consider we do not have the blue, just we have the yellow. In that case, we will have certain pressure. Now we are combining both the gases. In that case, these 5 molecules also occupying the same volume. These 10 molecules also occupying the same volume. Therefore, the number of molecules has increased. So they will have the possibility to collide each other even more. That means the total pressure will increase. Okay. But one thing, how much the pressure will increase? Just if we kept the molecules, only these 5 molecules in this container, how much pressure it will exert on the volume? That is the partial pressure of that component 1. And if we have another these 10 molecules inside this, just only that 10, in that case, how much pressure we will have? That will be the partial pressure of this component, and the total pressure of the system will be the partial pressure of this one and partial pressure of this one. So we will get the total pressure in this container. Just what was the pressure here and what was the pressure here, we will have the total pressure equals sum of the partial pressures of components, as many as components we have. So adding a gas to gas B increased number of particles, increased collision and pressure. So if you add two gases, you will get more number of molecules. So more number of collision. Therefore, you will get more number of more number of collisions. So the pressure will increase. Fraction of number of collision depends on fraction of total particles. So within the total, how many parts came from this or from this, that will depend on the fractional pressure. Whatever fraction of the number of collision depends on the fraction of total particles. Then Charles' law, what is? I remember like this way. Charles' law, that means there should be the as I learned or I have studied in Bengali medium, so I try to remember Charles' law. That means constant is pressure. That means in Bengali we call chap. Pressure is chap. So in Charles' law, that means it comes like a C, and in Bengali chap. Also we write down like a C. So I remember in Charles' law, chap is C, constant. That means pressure is constant. So here V proportional to T. That means if you have a container with many molecules, what? Yes. Yes, exactly. So Charles' law, that should be the pressure is constant. So if you have a container with number of molecules, in that case, if you increase the temperature, what will happen? If you have a, maybe let us consider we have a gas container like this and we have certain molecules and we are increasing the temperature using some lamp, or you can use some, not very good, I'm not doing. Anyway, I wanted to show some lamp. Okay. Anyway, so if you hit these gas molecules, what will happen? Everyone is perfect. So that is the way that everyone has different idea. So if you learn by yourself sitting somewhere, then you will be single directed. What your mind thinking or what you are thinking, you will not get different idea. So she told that the movement of the molecules will increase, and some of you have told that pressure will increase. Okay, both are fine. Actually, if we increase the temperature, first let us consider we are not giving the heat. As already we have mentioned in the kinetic energy theory or kinetic molecular theory, that time we have mentioned that all the gas molecules are moving randomly with a constant motion or constant speed. Okay. Now, if you increase the temperature, that means that will come as a energy. So that energy will come to the molecule. So if the molecule has more energy, their movement will increase. That means the kinetic energy will increase. Therefore, what will happen? They will try to, previously it has this mass space in between. Now, if we are giving more heat as energy, then what will happen? It can move maybe up to this, like this, so that the movement or the kinetic energy will increase. What is the time? When will our class? 8:20. Okay, we have enough time yet. Okay, so if we increase the temperature, then finally the volume will increase because we are increasing temperature and then the kinetic energy is increasing and the internal space between molecules will increase. Therefore, the volume will increase. But yes. Yes. So, in terms of pressure, if you keep the volume constant, if this system is closed system, in that case, there is no way that the molecule can escape from out inside to outside. In that case, the movement will increase, kinetic energy also increase, therefore the pressure will increase. So the number of collisions, the possibility of collision will increase. But if you have the container as open container or open system, in that case, you have the space to move the molecules escape. So in that case, we will consider that the volume will increase with the temperature. So kinetic energy increases with increasing temperature, increases in collision frequency, and increase in pressure. All of them are okay. The wall moves to increase volume and restore initial pressure. That means if you have some wall which is flexible, that means if you put some pressure or if you put some heat to the molecules, in that case, if the wall is rigid, like as this building wall, or any wall which is rigid, cannot be moved easily. Therefore, in that case, we will have the pressure will increase. But if the wall is flexible, just we are increasing the temperature, so the molecules are moving faster. Therefore, we can have the volume to increase. That means if we use the formula or if we mention the formula like this way, at constant pressure, if we put the constant pressure, that means we are allowing the wall to move, or we are considering the wall as flexible, so that at constant pressure, the volume of the substance volume of the gas is directly proportional to the temperature. That means if we increase the temperature, volume will increase. If we decrease the temperature, volume will go down. Okay. Should we move forward? Avogadro's law, that is little bit okay. What was the figure here? I think I don't need to explain, already explained quite a lot. Okay. Now, V proportional to N. That means volume, if you have a gas container with very large, number of molecules, we have a gas container. So, if we consider just half of the or 1/3, maybe 1/3 of the container, so how many molecules we have? Just if we consider all the gas molecules are staying everywhere. If you use some body spray or some scent, just everywhere, or everyone will get the smell. Maybe some of those who are very close, they can get little bit more, or someone who is little bit far away, they can get less, depending on the, maybe you have some time diffusion. So now, but we will get something. Maybe we cannot feel, however, we will have something. So if this gas molecule, if we have a small volume, we have here 1, 2, 3, 6, 7, or if we consider here this, maybe 8 molecules. just 1/3 of the container. That means, let us consider 1/3 of the volume of the container has 8 molecules. Then what would be the whole? More number of molecules. So that means we can consider easily that the number of molecules is directly proportional to the volume of the gas. That means if you have more volume of gas, you can have more number of molecules. So adding more particles increased number of collision, pressure increases, same thing. The wall moves to increase volume and restore initial pressure. Okay, and just anyway, we are considering if you add more number of molecules in a same container, that means open container. Here, what is the figure we are showing? We had few number of molecules. Now, this is a system or cylinder, gas cylinder. We are connecting this gas cylinder to this container so that we are adding some molecule to this. And this lid is little bit flexible. So when more number of molecules are adding to this container, in that case, this volume, that means this lid is flexible. So when the pressure is increasing, more number of molecules is adding here. So it is giving more pressure to the lid. So it is going up, and it is more number of molecules. So the volume has been increased. So we can say that the number of molecules is directly proportional to the volume of the gas. Different gas, same volume, same pressure. That is another thing. Okay. If you have different types of gas, like as hydrogen, oxygen, nitrogen, carbon dioxide, or any other gas, so that is little bit confusing. But if you can understand that easily, you can remove your confusion. So kinetic energy same at the same temperature for different gases. For any gas, if you have the same temperature of the system, if you put oxygen gas, carbon dioxide gas, nitrogen gas inside a container, same container, then if you keep the temperature of the system constant, then you will get the kinetic energy of all the gas molecules will be same. How it is possible? There are all different types of gases. How it is possible? Kinetic energy. Now, what is the equation for kinetic energy? Half into m. That means half mv square. Half mass velocity. Okay. I have more than 70 kilogram weight. Some of you maybe you have 35 or 40. Is around 45. Okay, that's good. That means almost half of me, or 2/3 maximum. Okay. Now, if you consider that if I try to run and you try to run, then you can have much faster speed compared to me. That is the idea. That means kinetic energy is not only related with the molecular mass, that is also related to the velocity or speed. So here we can see that kinetic energy is same at the same temperature. That means if any of the gas molecule, several types of gas molecules, if all the gas molecules have same temperature, then all the molecules will have the same kinetic energy. How it is possible? Heavy particles must move slowly. I cannot run very fast. Particles, molecules with a higher mass have on average a lower speed. So here you can see, now we can see. Okay. Sometimes, yeah. Magic. Projector? No. Anyway, if we could see both of them together, then we could use the cursor. Another thing, I have another cursor. Let's see. No. Those who are online, they can see my cursor, but none of you. Anyway, so what I'm going to say that if we have a very large molecule, that means heavy molecule, then it has some possibility with less velocity. So that means on an average, the kinetic energy becomes equal. So if we have a very small molecule like hydrogen, it can move very fast, and so we need to have the mass into velocity square then half. So that is the formula how we can count the kinetic energy. Therefore, for any types of molecules, if we have the same temperature, we will have the same kinetic energy. Okay, I'm not interested even. Thank you.